Hello everyone, I am Trivedi from LJ Institute of Engineering and Technology, and today we will learn the practical of static and dynamic balancing. This static and dynamic balancing practical comes in the dynamics of machinery subject. So let us start our practical. What is the aim of this practical? So the aim of this practical is static and dynamic balancing of rotating masses. So here we have to consider the static and dynamic balancing of rotating masses. So particularly it will show us how to balance the system or how to find out the unbalance of the system. So basically it is this only. Now let us start our introduction. So here as you see, this is our static and dynamic balancing apparatus. Okay, here there is a shaft. The V belt is attached with the pulley of the shaft, and there is a motor, and this motor is attached with the variac by which we will transfer the voltage. Now, for this system, we have to explain what the theory says. So, we have already learned about this theory. This is our different masses. We say 1, 2, 3 and 4 different masses are there. And we need to balance all 4 masses with 2 masses, A and B. Now because A and B are unknown masses, we can take A as a reference plane, and from this reference plane whatever the length, they are considering at the right hand side positive and left hand side negative. Now we have already the angles of these masses 1, 2, 3 and 4 are known to us. So here these are the angle of these masses. So mass m1 is at here, 2 at theta 2 angle, 3 at theta 3 angle and 4 at theta 4 angle. And different lengths with respect to A, it means 1 at L1 length, 2 at L2 length, 3 at L3 length, B at LB length and 4 at L4 length. This is also known as plane position as well as angular position of masses. So they both are the basic practical. Now let us make the table for it. Now in this case, because you all know, we have omitted or neglected the angular speed. Whatever the angular speed of a system, it will not create much effect on that system. Okay, only what is creating the effect, because omega is same for all, each and every mass, so we can omit it easily. So here we are taking the table of plane, mass, radius, centrifugal force, distance with reference plane, coupled by omega square and angle. So here for the planes 1, A, 2, 3, B and 4. Masses are M1, MA, M2, M3, MB and M4. Radiuses are R1, RA, R2, R3, RB and R4. And centrifugal forces, that is mass into radius by omega square is that. Okay, so here we can write M1 R1, MA RA, M2 R2, M3 R3, MB RB, M4 R4. Now distance from the plane A. So because 1 is at the opposite side, we have to take as minus L1. This is 0. A to A, it is 0. Then L2, L3, LB and L4. Now coupled by omega square. So here the product of force into length. So here minus M1 R1 L1. This is 0. M2 R2 L2. M3 R3 L3 as well as for each and every value. Now what are the angles? So angles for 1, 2, 3, 4 are known, but A and B are unknown. We only need to find out the values. So here theta 1, theta 2, 3 and 4 are known. A and theta B are unknown. So because we have this table, we can easily calculate this system with graphical as well as analytical method, which we have already studied in our theory session. In this case, I will explain the analytical and graphical both of this method, but with the practical values. So now let us start our practical. So for this, let us, as we all know, this is the variac and we have to increase the speed of the variac. Now here, first of all, let us check the balancing machine, balancing check of the machine without the masses. So here we didn't put any mass on the shaft. Okay, and if we see, there is not any kind of vibration or motion for this machinery. It means the total machine, the shaft is completely balanced. Okay, so we have checked the system for the balancing without the masses. Okay, now let us start the let us see, these are the balancing masses which we have to put on this shaft. Okay, so these are the masses. They are having different weight. I will tell you what weight at what radius. So here these are the different masses. They are of the steel material and we have to attach on this shaft. So what is the procedure for this practical? First of all, yes, I told you the procedure with respect to the data. So here, first draw the space diagram. It means we have to draw the space diagram where the masses are placed. Let me show you what is the space diagram. This is known as planes position diagram. This is known as space diagram. If you draw it, it will be very clear in your mind that how to solve the data. Okay, so this is the space diagram as well as angular position diagram, and then you have to make this table form. Okay, now we have to find out the centrifugal force for each mass. It means simply make a table and note down the values on the masses. So and radius calculation, and we are getting the centrifugal force as well. Now we need to draw the vector diagram. It means the space diagram for the angular position, and then we need to arrange the masses on the shaft with the help of the spirit level provider equipment. Okay, then we have to switch on the motor and slowly increase the speed. Okay, so let us check what happened, and then we need to calculate the unbalanced couple as well as forces generated on the shaft. So for this, let us have the practical initialization. So here we have attached a single mass at here. If you see in this in this video, there is a system and we have attached a mass at here. Okay, now let us give the rotation to this mass. Now by giving the rotation to this mass, what will happen? Now slightly increasing the speed, and if you can see, there are slight vibrations, slight jerk in our values. Okay, these are the jerks in our values. So by adding only a single mass, we are getting the jerk in our machinery. Now let us have the another practical procedure, and in this we are attaching two masses. Okay, so here in our case we have attached two masses. Now by giving the speed to this system with the rotation, so let us give the rotations. So by giving the rotations to the system, if you see here, you can see the vibration. See, okay, so we are only attaching two masses and it vibrates like anything. Now in the next one, third one, let us attach the three masses on the system. If you see, let us compare. This is for without the system, without the speed, and here sorry, this is the steady condition, and at here if you see, by putting the three masses it will vibrate like anything. And if you want to listen the sound, I can play it. Listen the sound. So in this case, if you see, it vibrates like anything. Now, what is the reason for the vibration? The reason for this vibration is because the unbalance is there. Okay, so now let us calculate. Now, if you see the shaft at here, it is fixed at here and it is rotating, but it doesn't vibrate because it is completely balanced, and as well as it will not create any sound. Now for this, let us make the data. First of all, we can easily find out the position. of the masses. Okay, then the position of the planes. It means we have to draw both of it, A, B and C masses. So here we'll take A as a reference plane, B and C as equidistance from our position. It means 80 mm. Now angular positions of the mass. So mass A is randomly put at 320 degree, mass B at 90 degree and C at 200 degree. So these are the basic space diagram. Now let us have the table values. So here planes. So A, B, C, there are three planes, masses. So these are the masses. Mass A is 0.270, mass B is 0.3 and C is 0.445. Now what are the radius? So here the radius is 0.02 meter, then 0.03 meter and C is again 0.02 meter. Now what is the centrifugal force by omega square? So simply we have to multiply mass with the radius and we are getting centrifugal force. Now student, we are not calculating the force in Newton meter. Now what is the reason? Because we divide it with omega square. We will not get the value in Newton. Okay. Now distance from the reference plane, it is 0. It is 0.08 and it is 0.16. Whatever we have calculated. Now here couple by omega square and here the couple by omega square value we need to calculate as this and these are the angles. Now we can solve this with graphical as well as analytical method. For this for the graphical method we have to take this as a center line or first of all, let us mark the O point. So this is O dash point. Because we are taking A as a reference plane, we cannot calculate it. So here O dash B dash, draw the O dash B dash vector, whatever the value, and then O dash C dash vector at 200 degree according to that value. Now here we are getting unbalanced force in this direction. Okay, so this is unbalanced couple value. Now we can compare the graphical as well as analytical method both. So for the analytical method, as we all know, we have already aware about the equation. So here couple horizontal. The equation is CB cos theta B plus CC cos theta C. By putting the values, we will get horizontal couple as minus 1.338 into 10 raised to minus 3. Similarly, we have to calculate the couple vertical and that value we will get as 6.71 into 10 raised to minus 3. Now let us calculate the resultant value and the resultant is 6.84 into 10 raised to minus 3 kg meter square. If you calculate this, if you take the scale and draw this diagram, it is exactly same whatever you are getting in couple resultant. So this is the couple value which is unbalanced and by that we are getting the tremendous sound as well as the vibration on the system. Now let us have what is the value of force polygon. So here this is the force polygon. In this case we have to mark first O. Okay, then we have to mark B, O to B at here. Then we have to draw force of C. So let us mark C. Then we have to draw A. So this is A and this is the unbalanced force whatever we are getting. Now if we calculate the unbalanced force, that unbalanced force is approximately we will get as 4.89 into 10 raised to minus 3. This is not in Newton, it is in kg meter. Okay, so we will get the value in kg meter. Now let us have the analytical method. We have to draw the analytical method analytically solved similar as the couple values. So force horizontal. So in this case Fa cos theta A plus Fp cos theta B plus Fc cos theta C. By putting all these values we will get horizontal value is minus 4.22 into 10 raised to minus 3. Similarly for force vertical we will get the value as 2.48 into 10 raised to minus 3. So finally, resultant force value we are getting as 4.89 into 10 raised to minus 3 kg meter. So this is the force polygon, and this is the unbalanced force value what we are getting in our balancing machine. Okay, now this is for our theory data, and we compare the theory as well as the practical. So this is our static and dynamic balancing machine apparatus. Thank you so much all of you. If you have any query, feel free to ask me. Thank you.